When we left off last time, we had started constructing the virtual machine, and the next focus is going to be on implementing some of the instructions, some of the opcodes. And before we get started, I realized that one thing that we're missing that we're going to need pretty quickly is the concept of local variables. The last time we created the stack, the heap, the program counter, and the method area, and we're missing the local variables. And very quickly we're gonna need that, because pretty much about half of the instructions will use that, of the ones, at least of the ones we're going to be creating today. And it's a very fundamental data structure. So let's go ahead and do that. We're going to just create a stub for that for now. And right now we're just going to leave this as an empty data structure, and we'll fill in the details as we get to it. So as we begin our next exercise, which is going to be implementing some of these instructions, first thing we're going to want to do is go to the virtual machine spec and understand how these instructions are documented. And I think this will help us in understanding how to implement all of the instructions. So the way they're documented is each instruction has something called a mnemonic. This is basically just the name of the opcode, a short description of what that opcode does, and then a format. And the format is the way the bytes for that opcode are implemented. Now, some instructions are just 1 byte long. They have a single byte that identifies that opcode. The machine goes off and does what it needs to do, and you have a nice day. Other instructions are a little bit more complicated, and you need a byte to tell the computer what to do, and you also want to attach to that instruction some additional parameters, or bytecode. They call them operands. And those just give the machine additional information about how to execute that particular instruction. The next area here of interest is how that particular opcode affects the stack. And the way this is documented is it shows the value, it shows the state of the stack before the operation. In this case, we have 2 values sitting there on the stack. Then the arrow shows you what happens next. So we start out with value 1 and value 2 on the stack, and this instruction will need to pop those 2 values off of the stack, manipulate them in some way, and then push a different value back onto the stack. And then there's some additional information for each instruction about what it does, so a detailed description of what it does and how it should operate, and some information about exceptional conditions that might occur, linking exceptions and other runtime conditions that may occur. For example, a divide by 0 exception in the case of a division operation. You might say that it takes value 1, divides it by value 2, and pushes the result onto the stack. And then maybe there's some condition that happens if value 2 is equal to 0. Divide by 0 exception may be thrown. So information about that will be described in these exception area. So without further ado, let's go ahead and start looking at some instructions. What we're going to do is we're going to start out with the simplest possible instructions in the machine, dealing with integers. So we're going to want the machine to be able to load an integer from the local variables. We're going to want it to add 2 integers together. We're going to want it to check a condition to see if an integer is equal to 0. And we're also going to want to store an integer back into a local variable at some point. So those are the instructions we're going to aim for. Let's start with the load and see how we want to model this in software. We have a load operation. Its value is 21, and then it has an index. So the description is to load an integer from a local variable, and it's going to load it onto the stack. So before the instruction executes, there's a bunch of stuff on the stack. After it executes, there's a bunch of stuff on the stack, plus this new value that we've just pushed onto the stack. The secondary opcode parameter, this index, is an unsigned byte that must be an index into the local variable array of the current frame. The local variable must contain an integer, and the value of that integer is pushed onto the stack. All right. So what we're going to do is we're going to create an object that represents an instruction in the generic sense. And then we're going to implement one of those for every instruction that we come across. So what we're going to want is an instruction, and what we're going to want to specify about it is the name of that instruction. We're also going to want to specify the bytecode that identifies it, in this case 21. We'll call that the opcode. We're also going to want to tell the system how long this instruction is. In this case, it's 2 bytes. The first byte being the ILOAD and the second byte being the index. So we're going to give it a length. And the third thing we're going to do is give it a function that is what function this opcode should execute every time we come across it. And we're going to call this the execution function. We'll see how that comes into play in a minute. So for now, we'll just say obj equals this. We'll create our usual constructor, return obj. And we'll hook up the variables. Obj.name equals name, obj.length equals length, obj.opcode equals opcode, obj.execution function equals execution function. That's great, but we haven't really done anything except create an object that represents each instruction. And we're going to want a collection of these, one for every opcode. So what we want is a container. Whoa, what's going on there? Okay. And so this is going to be our container for all of the opcodes. So since this is a container, we need some data structure to hold it. So we'll just say obj.table equals an empty table, and we're going to create a method to add new opcodes to this table. So we'll say add opcode, and we're going to give it the same spec that we gave for the opcode. Equals function, it's going to take a name, an opcode, a length, and an execution function. And we'll say table obj.table opcode equals new JVM instruction, name, opcode, length, execution function. There we are. And semicolon. Splendid. All right, now we need a few instructions. So let's go ahead and say var opcodes. Actually, let's do it this way. So we've created this JVM opcodes object, but it's not really connected to anything. And what we want to do is connect it to the virtual machine. So the virtual machine has access. So we'll instantiate that object here, and we need a way to initialize them and actually set up those opcodes. So let's go ahead and do that here. obj.opcodes.add opcode, and let's look at the ones we want to implement. Well, the first one we want to do is ILOAD. This is instruction number 21. It is 2 bytes long, and we want to give it some function to execute whenever that opcode is encountered. So I'm just going to leave that as a stub for now. We'll implement that in a couple of minutes. But in the meantime, let's go ahead and add the remainder of the opcodes that we're going to add today. We're going to do an ISTORE. That's LSTORE, that's not quite right. Where is ISTORE? Is here. So this is opcode 54. This is also 2 bytes long. And this is ISTORE function. Whatever we want to execute when that happens, obj.opcodes add opcode. We wanted to do IADD because we want to add 2 integers together. So this is 96. This one is only 1 byte long. And finally, we want to do a conditional jump. So we're going to say if condition and we'll say this is if equal. This will be 153, and this one is 3 bytes long, the opcode, and then 2 branch addresses that we want to jump to, depending on that condition. So this one's 3 bytes long, and we'll call this underscore if equal function. So now we've got this table of opcodes, and each opcode is associated with a function that we want to execute when that opcode is executed. Well, that's great. We still need to implement these functions to tell each of these opcodes what to do. So let's go ahead and do that now. I'm gonna go ahead and locate these at the bottom. We'll say function underscore ILOAD function. Now, what do we want this function to operate on? Well, it may manipulate any aspect of the virtual machine. So it may access the stack, the heap, the method area, probably not other opcodes, although that would be an amusing exercise. So it makes sense just to pass the virtual machine itself as an argument to this function. So we'll pass the virtual machine itself. Now that's not all it may need to access. It probably also needs access to what we'll call the operands, or this list of extra information that comes along with the opcode. So what we're going to do is we're going to pass an array with the agreement that that array should contain the opcode plus any other bytes that go along with that opcode, the opcode operands. And that's what each of these functions needs to take as an argument. So this is going to be ISTORE function. It's going to take a virtual machine, operands. And we're also going to want IADD function, VM operands. And finally, if equals. Oh, there's actually one other piece of information that would be useful in these instructions, and that is the definition of the instruction itself, or this object that represents that instruction. So we'll go ahead and add that as one of the arguments to each of these. And so this will be the set of all possible input and output that these instructions might want to operate on. So now let's focus our attention on the ILOAD function. So let's go back in the spec and look at that ILOAD in a little bit more detail. So load an integer from a local variable. We get the index of the local variable that we want to load the data from, and we want to push that onto the operand stack. Index is an unsigned byte that's an index into the local variable array, and the local variable must contain an int. The value of that is pushed onto the operand stack. So let's see if we can implement that. So we want to first start out by getting this index. So we'll say var index equals operands 1. That means this operands is this list, and it should contain 21, which is the first opcode. And then it should contain that index at offset 1. So we get that. Index is used to get a variable from the local variables. So we can access the local variables by saying vm.local variables, and we want to get an integer. And we want to get a particular integer at that index. And we'll call that value. What we want to do with that is push that onto the operand stack. So let's do exactly that. So we say vm.stack.push integer value. And that pretty much finishes that instruction. And we haven't implemented these two methods that we call the get integer and push integer. So we'll have to remember to come back and implement those. But let's go ahead now and move on. Let's just pretend that we've implemented those, and let's move on to the store. Well, the store is going to do just the reverse of this. It's going to pop a value off of the stack and then store that in the local variables at that same index. So the first thing we're going to do is say our value equals vm.stack.pop integer. It's going to pull that value off the top of the stack. And what we're going to do is we're going to construct that same index. And now what we're going to do is vm.localVariables.put, let's say set integer, and integer value. So what we've done is popped it off the stack. We've gotten an index in the local array and then store it back into the local variables. Cool, that seems simple enough. Well, let's look at the add function. Well, the add function does something a little bit different. It has no additional arguments. That's cool. What it does is it pops two values off of the stack. So we have value 1 and value 2 on the stack. it's then going to add those two together, and it's going to push the result back onto the stack. So let's see if we can do that. So let's say var value1 equals vm.stack.pop integer. That's going to pop the first one off the stack. Var value2 equals vm.stack.pop integer. Do that again. And now we want to add those two together to make a result. So we'll say the result is value1 plus value2. What we want to do with that is push it back onto the stack. vm.stack.push integer result. And now we have implemented our add instruction. Now finally, we have an if equals function that we want to implement. So what this does is it pops the value off of the stack, and then it compares it with 0. And if it is equal to 0, then we're going to jump to a new location that's specified by these branch bytes. And if it's not equal to 0, if this comparison fails, then we will simply drop down to the next instruction. So let's see how to implement that. So we'll follow the same pattern. Var value equals vm.stack.pop integer. Pop that off the stack. Got an extra dot there, that's no good. All right, so now we want to do a comparison. If value is equal to 0, then we want to jump to a location that's specified by these branch bytes. How does this work? What it does is, if the comparison succeeds, branch byte 1 and 2 are used to create a signed 16-bit offset, where the offset is calculated to be branch byte 1 shifted by 8 bits, ORed with branch byte 2. So what we're doing is making a 16-bit integer out of two 8-bit integers here. So we'll say offset is branch byte 1 shifted by 8, ORed with branch byte 2, and that's our offset. And this execution proceeds at that offset from the current instruction. Okay, so vm.stack. So we get the current instruction, which is the program counter, plus this offset, and that becomes the new address. So what we're going to do is update the program counter to be that new jump address. Now, one thing we've glossed over in the last couple of instructions is what to do in the else case. Well, the else case, we want the program to proceed not from the jump address, but from the next instruction. Now, if we didn't update the program counter, then what would happen is we would execute the instruction, and the program counter would be the same, and so we would come back around and execute the same instruction again, and then execute the same instruction again, and the machine really wouldn't get anywhere. So for each of these instructions, we actually have to update the program counter to point to the next instruction. Well, how do I know what the next instruction is? Well, I could just say add 1 to that. Just increment the program counter by 1. But the difficulty that I have in that approach is that not all instructions are 1 byte long. Some of the instructions are 1 byte, some of them are longer, some of them are shorter. And so what I really need to know is how long that instruction is. Well, fortunately, we have an object that tells us information about how long each instruction is. That's this instruction, which has a member variable called length. So let's go ahead and do that. We'll say program counter equals program counter plus instruction.length. And that will update the program counter to point to the next instruction, whatever happens to be there. So that will be what we do in the else case. And of course, for the add and load and store instructions, we need to do the same thing. Every time we complete the instruction, we need to move on to the next instruction. Now the only thing remaining at this point is that we have these methods for the stack and the local variables that we need to implement. In particular, we need to, for the local variables, we need a get integer and a set integer, and then for the stack, we're going to need a push operation and a pop operation. So let's go ahead and implement those, and that should complete the implementation of these methods, of these opcodes, I mean. So our local variables, we need two operations. We're going to say obj.set integer. And that's going to be a function that takes an index and a value that we're going to set as the integer value. Obj.getInteger is a function. We're going to give it an index, and it's going to return the value for us. So what we will need here is an object that holds those values, and we're just going to make that a table, a hash table, and we will say obj.values at this index, and we're going to assign that to value. Then for the get integer, it's very similar. Obj.values at index is what we're going to return back to the caller. Now for the stack, we also need a push and a pop. Push integer and of course we need something to push it into, so we'll say obj.stack equals, in this case we're going to make it a list or an array. And the way the push is going to operate is we're just going to say obj.stack.push value, and the pop is just going to be the reverse of that. Obj.pop integer equals function value, no value, and this is going to do a return on obj.stack.pop to return that. All right. So at this point, we've implemented all of the pieces that we should need to make this this 4-instruction virtual machine operate. Now, we have yet to program it and to actually try to run it, but I think it's time to go ahead and wrap up this video, and we'll save that for next time. So what we'll be doing next time is programming the virtual machine by creating instances of these opcodes, putting them in the method area, and arranging for the apparatus necessary to go ahead and execute those instructions. And along the way, we'll probably revisit the user interface because once we start executing the virtual machine, we're going to find it handy to be able to visualize what's going on inside as we step through each of the operations. So I'll go ahead and wrap it up for today. Thank you for watching, and we'll see you next time.